Uh, if you observe this materials, one is copper and tantalum. So this is my application for one of the sector. So I want to deposit copper and tantalum. So there is a huge difference in melting point temperatures in both the cases. So it is very impossible to deposit through direct energy or powder based fusion process. Only the feasible solution is friction stir additive manufacturing. So that is the advantage of solid state additive manufacturing facility. So you can build dissimilar kind of materials for different applications. So copper and tantalum and copper and niobium also. So you can also build these kind of materials. So very just an overview of this slide is you can get better mechanical properties, less porosity, less energy, and compatibility with the dissimilar kind of materials, and no gases are required to protect the contamination from the environment. So and stresses which are included in the material or development of the material is less, because in fusion based additive manufacturing you are melting the material and allowed to solidify. During the solidification process, that is a rapid solidification process, because the diameter of the nozzle is 0.2 mm diameter. So you can print the material of 0.2 mm diameter of the liquid metal droplets. Once droplet is deposited onto the substrate, you have a environment that is 24 degrees centigrade. This droplet temperature is around 3000 degrees centigrade. There is a huge difference in the temperature. The quick heat transfer takes place to the surrounding. Due to that, this solidified material becomes brittle. So that is the drawback in additive manufacturing process. So directly you cannot use the component for applications because of this problem. The problem is, even your ductile nature of the material, after printing it becomes low ductile. You need to enhance the same ductility of the original material. You need to go for post-processing process. The post-processing process is essential for any additive manufacturing component. Right. Sometimes post-processing is not possible certain materials. For example, in case of aluminum alloy, 2024 is not respond to heat treatment process. So once the material is not respond to heat treatment process, after building the additive manufacturing component, the component properties are inferior to the existing material. Then you need to compromise the properties of material when you are going for additive manufacturing process. Okay. So suppose if it is a complex geometry, there is no other way to build the component using the same material, then you need to compromise. So the limitations, what do you expect the limitations? Because you need to apply the rotation and you need to apply the force onto the tool. Then only it will build the component, either friction stir additive manufacturing or friction stir deposition. So once you are building the certain height, there should be a buckling action because you are applying the force downward. Due to that, there should be buckle. So the limited height is possible only this process, not beyond certain equivalent to the additive manufacturing process or powder bed fusion process. There are also some issues with the when you are going very high, bottom should be overheated, because you are adding the material layer by layer. What is happening at the bottom? always heat is supplied to the bottom portion. The bottom portion becomes coarser, the top portion becomes finer. So there is a mismatch between the properties between the top to bottom of that components. So once you apply the heat treatment of the entire component, that properties are come back to original position, then there is no issue of these. And this is also one of the MTech student has done his MTech thesis on development of functional graded material using the different materials. In example, sufficient stiffeners built by FSAM process. These are the properties which are generated through 6061 and 5083. Yeah, coming to wire arc additive manufacturing. So now I am talking about fusion based additive manufacturing process. Means you are melting the material during the development of the component. So this is wire arc additive manufacturing. This was patented in 1920. Yes, you can see now last 15 years we are talking about additive manufacturing, but 1920 itself the patent is granted towards additive manufacturing facility. So why we are lagging from 1920 to this year is because of CAD/CAM. So you need to integrate your deposition nozzle to the XY plotter. So that is a gap from 1920 to this. So once the CAD/CAM is developed, then you need to integrate this nozzle to the XY plotter so that you can develop the component. So because of this, then you have n number of synonyms related to each and every technology. Depends upon the manufacturers. They can do the business on the name of that process. So just you can see this diagram, welding deposition, welding based rapid prototyping, 3D welding, 3D micro welding, near net shaping, hybrid layered materials, shape deposition modeling, etc. So you can see all over the world people are using wire arc additive manufacturing process because it gives very useful to the industrial applications, especially large bridges, large structures. You want to build the large structure using this technology. So nowadays entire ship is built by wire arc additive manufacturing process. So earlier, if you want to make a ship, it takes 2-3 years to complete the process. Whereas using this technology, it may take 6 to 7 months to complete the entire ship. So the mostly South Korea, one of my PhD student went for PDF doing the technology, using the technology, that is automation of spot welding process. So South Korea is in front of all the countries compared to the other technologies. The wire arc additive manufacturing facility is very useful for them. So it is a simple process. Just you are integrating with the robot. So you are initially just you take the manual GTAW process. You have a gas junction arc. You have filler wire. Then you are melting the filler wire and deposit onto that substrate. So you can do manually with some limited length and some limited structures only. Suppose if you want to build in this type of component, then you need to go through the automation of the process. Only thing is this torch is attached to the end of the robot arm, so that is enough for my job to complete the process. So first I need to generate the path as per the requirement. Initial path is different, the top side path is different. So once you integrate this path combination with the torch movement, then you can melt the filler wire and deposit onto the substrate, so that you can able to get the component. So here the knowledge is required, robotic language. So you need to convert your CAD file or CAD data to robotic language, because robotic language is understood by the robot only. So once you give the program to the robot, automatically it can does the operations. Okay. So in our COE, BTech students are doing this kind of wavy kind of pattern. So normally linear welding, circular welding. So linear welding you can do it easily with robot programming, and circular also you can do it. But if it is this kind of wavy kind of structure, so it requires CAD knowledge and requires mathematics background, so that you can generate the coordinates of this fashion. That coordinates you are integrated with your robot. The robot can easily move in this fashion. Okay, so BTech second year students are doing this kind of work. So they will generate only path planning of a robot. That is enough. So path planning is you are getting as per your CAD file, then you can able to generate the components. The latest trend in wider arc additive manufacturing, because for developing the path planning for complex geometries, it is very difficult. Okay, so in additive manufacturing, you have a CAD file, then convert into STL file. That STL file can understand the AM machine. Here, you are generating the path planning using robotic language. So instead of that, why don't you interface with the CAD? So you have a CAD geometry, you have a robotic language. So you need to generate the interface between these, then your problem is solved. So whatever the CAD data, that will be converted into robotic language by the interface. Then you can able to run the program very easily. So this is the latest trend in WAM process. Okay, so you can do n number of projects if you are good at mathematics and CAD. N number of projects with a simple robot. You can purchase a robot worth of, let us say, 5 to 6 lakhs. You can generate on your own programs. Some different curvatures, I want to weld this different curvatures. You need to generate the programming using robotic language. So the videos are not playing. Why? Yeah. So this is I am only concerned with the problems. Okay. So these are the different materials: titanium, aluminium, steel, nickel-based alloy, and bimetallic. These are the materials are available for printing using wire arc additive manufacturing process. So the basically additive manufacturing, frankly speaking, it requires a lot of knowledge in metallurgy. So without metallurgy, you cannot be called as a additive manufacturing engineer. So without that, we cannot do anything. Okay. So first of all, I have a aluminum material. Then I have a project. I want to print a component using aluminum material. For that, I need to study the literature review related to aluminum alloys. When you are printing the material, what are the problems encountered? That you need to address first. So once you know the problems, then you can search for the solution for that problem. So once a solution is there with you, then you will be in front of others. Now you take aluminium, just you can see the aluminium. The number 5 shows high problems. The number 5, that porosity is the major concern, right? In one of the material that is related to aluminium. So if you weld any aluminum material, porosity is must. Without porosity, you cannot build the material. Then how to reduce the porosity? That is my concern. So to reduce porosity, how the porosity is come into picture? That you need to know that. So once you are welding in an open atmosphere, that metal is melted, the gases surrounding by you is absorbed by that liquid metal. Okay, so once you are doing welding or printing of the material using VAM process in open atmosphere, you may get porosity. That is the reason. Then how to rectify that? You can provide some atmosphere, that is argon or helium or combination of these two. So once you provide the organic atmosphere, there will not be gases entrapped during the printing process. That means your oxidation problem is minimized, not, we cannot say eliminated, minimized. So if it is minimized, you are better than the previous one. So that is a solution for this one. In some cases, oxidation is another issue in the case of titanium. If you want to weld titanium or if you want to machine titanium, there is a problem with the oxidation. So titanium is immediately react with the environment when it reaches to certain temperature. That is titanium dioxide is formed. So titanium dioxide is a very brittle material compared to titanium alloy. So titanium alloy is ductile. Titanium dioxide is brittle material. Then you have a combination with the brittle and ductile. The application, nobody will take your component. Then how to avoid this? Same solution is you can provide organic atmosphere. So one of my students is facing lot of problems when he want to print welding titanium using FSW process itself. So during FSW process, he is after welding immediately cracks. Then sometimes he may get inferior properties. Once you see the structure, then there are a lot of porosity in that. So due to that, get the inferior property. So the failure is also a problem. So people think that always getting the positive solution is not a problem, not a best PhD. If you complete the problems to solution is the best PhD. So like that, one of my MTech is completely done on failure analysis of copper to aluminium. So finally he succeeded at the end of his project. The solution is there are three precipitates are formed during combination of these two materials, Al2Cu, Al4Cu3, Al2Cu3. So because of these precipitates related to cracking. So once weld is completed, within fraction of seconds it will separate. Then you take the sample, then you can go for XRD, then you may get different phases. Then after identifying the phases, then you can go for the literature of these phases. What are the properties of these phases? So Al2Cu is brittle, Al4Cu3 is little more brittle, and Al2Cu3 is little more brittle. So once you avoid the Al2Cu3 and Al4Cu3, I may get a solution. Then you can also see the properties of these three phases. At what temperature these three are formed? These three are formed independent temperature, not same temperature. In one particular temperature, Al2C is formed. At another temperature, Al4Cu3 is formed. So if I am not going to that particular temperature, I may not get Al4Cu3. Isn't it? Suppose the temperature is, let us say, 200 degrees centigrade, AL force E3 is formed. If I am not going to 200, AL force is not there. Okay, so during welding process, you have to cool the material by providing certain environment, either liquid nitrogen or dry ice or water circulation. During that, the temperature is not reaches to 200 degrees centigrade. So once 200 is not there, your AL4CE3 is not there. Only Al2C is there. Then there will not be any crack. That is the solution. Okay. So from the failure, you can get n number of solutions, n number of answers, n number of projects, n number of patents. Okay. But you have to bear with the time factor. Time consuming is more. Knowledge is also improved lot. Okay. So same problem he will be continuing with other materials. He got a PhD. Not in NIT, some other foreign country. So with this knowledge, so what is his attitude is, I appreciate his attitude actually. Once the weld is completed, then I ask you to take the microstructure. The next day you will come with the microstructure. So how much effort gone into this to get the microstructure? So to get the microstructure, it takes at least 1-2 days. If you put hard work during the polishing and other things. So that's why he is completed within the period. It is MTech dissertation work. So like this problems, once you identify the problems, then you can get the solution, then you can get the degree. That is not a easy. So the parameters are nothing. Parameters are same as the welding process. Same voltage, current, wire speed rate, everything same. There is no change. Only change in your thinking. That's all. How to implement in the technology for getting the products. Then coming to this solution. So if you observe these two categories, now your welding head is attached to the robot. Then this, but the bottom you are melting the wire. So due to the gravity, that droplet is coming onto the substrate. Once you look at the first figure and second figure. So my target is, let us say, onto the camera, that red spot. I want to deposit the material onto the red spot of the camera. But due to the first case, it will not deposit. It will deposit either above or below. Naturally below, due to the gravity. So my target is missing. Suppose if I take a miniature component in printed circuit board, I want to deposit at a particular location. That is very precision, very important point of deposition. So due to the first mode, I am deviating from the location. So if you are deposited other than the position, your component is gone. Again you take the fresh component. That cost is very high. So that precision is very important to deposit the material. So the first case, the free flight mode of metal transfer, and the second one is short circuit transfer. So in the second case, your target is reached. Okay, you are depositing the material, not exact, it reached to that position. So based on your experience, you may adjust your nozzle position. Then due to the gravity, you are depositing the material. Let us say you are depositing material like this. After a certain height, due to the gravity, the material in liquid form still not solidified, it will be going down due to sagging. So due to that, you are wasting the material because you have to finish the component before sending to the applications. You are wasting the material. So that's why the direction of deposition is also important concept. So you develop the component in 3D and you can deposit the material horizontal, vertical, or any other fashion or combination of these fashions also. This is the real components. Yeah, this is lattice structures. Yeah, this is one of project work. This facility is available in the NIT Warangal. This synchro feed, what it does, so in normal welding process, just you are melting the material and you are feeding the wire, continuously you are feeding the wire to the down, right? So some technology, that is cold metal transfer welding. Have you heard of this word? What it means? It is same as your MIG welding process. There is no difference in the deposition of the material and the gun and other. Only the difference in the power circuit. Okay. So what they do is, once that electrode is protruded from the bottom of the gun, you have sufficient gap, the arc is initiated because of applied voltage and current. Arc is initiation. So due to the arc, the wire is melted, and the wire is melted, and due to the gravity, that melted metal is deposited on the substrate. And the next action, there is a time lag between the two depositions, maybe 10 seconds or 10 milliseconds sometimes. Okay, that gap, even then that gap is doesn't require melting of the material, doesn't require any heat for melting the material. Okay, so due to the gap, you are supplying the heat continuously. That heat is supplied continuously to the process. So due to that, accumulation of heat is more at the bottom. So what they do is, due to that 10 milliseconds period, the wire is retracted, just going back. So once electrode is going back, arc is not initiation. That you cannot see under naked eye. If it is highly magnified lenses only, you can see that fraction of seconds that wire is arc is vanishes. So that millisecond for one pulse, let us say, if it is 1000 or 10,000 lakhs, multiply by millisecond, it gives seconds. So that the amount of heat input is reduced. That is the advantage. So the amount of heat input reduced means there may chances of reducing the distortion of the material. For example, I want to weld, let us say, 1 mm thickness sheet. If I give a job to you, 1 mm thickness and 6 mm thickness, 6 mm thickness fellow is very happy than 1 mm thickness fellow, because there will not be a less distortion. 1 mm you have a large distortion because of you are supplying the heat input continuously. So once weld is completed, if you have a large distortion, then again you have to go for other forming process. That is secondary process is required. So to avoid that, why don't you minimize the distortion? So to minimize the distortion, what should I do? I have to supply the heat not continuously. So once you are giving the technology retractive feeding of with milliseconds, the arc is not initiated, when the arc is not initiated, heat is not generated, the amount of heat accumulation is less compared to old technology. So you can reduce the amount of distortion. So you can weld even 1 mm, even 0.1 mm also you can weld. So that technology used in Maruti and other automobile companies. Okay. Yeah. So this reiterative kind of welding facility, so that you can build the component and you can characterize the deposited material, and also then coming to the last slide, hybrid and additive manufacturing process. You are building the component, like in previous case, let us say. Yeah, in the previous case, you need to machine. So you are building the component and machining the component. So in one go, you can complete this process. So that's why in hybrid manufacturing, you are additive manufacturing and subtractive manufacturing. You are adding the material by melting the filler wire and layer by layer. And after deposition, you need to finish the component. For that, you need to remove this unwanted material from the deposited component. That's why you can go for subtractive manufacturing process. So both the combination of additive and subtractive together in a single machine, so that you can save setup time. Okay. So that you can reduce the lead time. So that is known as hybrid manufacturing process. You can play. Yeah. Yeah, this is direct energy deposition. Yeah, in this electron beam as a source and laser beam as a source. There are advantages of each and every process and limitations of each and every process also. Suppose for example, if it is a laser beam power source. So laser beam cannot be used for all the materials, because suppose for example aluminum as a work material, if we are using laser beam, the aluminum is highly reflective materials, so laser will be incident onto the material, it will be reflected back. So the amount of energy is transferred to the surrounding, not to the inside material. So the absorbing capacity of the material is required in the case of laser as an energy source. That is a major limitation. In case of electron beam welding, the material should be a conductive. Electron beam welding as a source, electron beam as a source, for that the material should be a conductive nature. Non-conductive materials cannot be done in electron beam as a source. Is it possible to play the video? Screen. No. Yeah. The arc is used to melt the material. Okay. Yeah. So there are two nozzles in the center, laser beam. I want to show you that VAM. Yeah, this is also one of the recent technology to prepare lattice structures. So lattice structures generally space grid structures which can be used for aerospace or defense applications for reducing the weight of the entire missile. So these are the space grid structure. You have let us say one sheet, other sheet. In between, you are developing this lattice structure to strengthen the entire system. So using the wire arc additive manufacturing, you can develop these lattice structures. So I think with this I can stop at this junction. You have any queries? Let me know. So just this is powder bed fusion process. Yeah, you can have any queries. Please free to ask. Students, you are coming late.
Sir, we are talking about wire arc additive manufacturing. So right now, what is the research area for the integration of CAD with the robotic language? At what stage we are?
So far, we are not used. It is in the implementation stage only. In Western countries, they are using, but not in India.
You told us in South Korea.
People are using.
So
Not
in India,
in, no.
So for that we need to develop the package, software package.
Yeah, software solutions are providing this interface between the CAD file and the robotic language. Then you can do it automatically with the help of the CAD file.
So actually in the early 1920 they patented.
Yeah, that technology, WAM process. After integration of CAD CAM only, they are come into picture. Yeah, any more questions?
For adding dissimilar materials, that is welding. So what are the properties that we need to consider?
So first of all, what I said is intermetallic components are very important role. For example, aluminium and steel, no? Aluminum and copper. AL to CU example I have given. First, you need to identify what are the phases that are formed for welding of dissimilar materials. Then you need to know the each phase properties. Once know the property, then only you can see that which phases he is going to eliminate by doing some alternative process or alternative techniques.
So how the bonding of these two dissimilar metals?
That means suppose Al to Cu is will not create any problem. Al4Ca3 creates a problem because that is a very brittle material. You are having a very ductile material. So there will not be compatibility between the ductile and brittle material. So that's the problem, it cracks. So you should know the properties of the phases first. Then how to eliminate the phases, also important.
So, can I know about what is the topology optimization?
Yeah, topology optimization is actually, for example, I have given you conversion area of circle, but I don't know the area of circle. I know the area of triangle. So with the triangle only, I can generate the approximate area of the circle.
Finite element.
Finite element. So you convert the circle into number of triangles. Because of the conversion, there is some area is missing. First, you can do the topology optimization. You can get that area also, so that you can error is minimized. Actual to real error is minimized. So for lattice structures, for example, you need to generate a curve type. For that, topology optimization is required. Otherwise, you may get lot of error. Real product to actual product. Yeah. Thank you.
Last question.
Yeah.
So we make components with automated, and also we make this powder bed form. Okay. In powder method, we can add different elements. Okay, but manufacturing is somewhat difficult. Whereas here manufacturing is easy. Can I add different elements, metallic, non-metallic?
That is bimetallic. That one of the paper is going to discuss. Okay. Bimetallic also we can do. That is that depends upon the metallurgical compatibility. In powder metallurgy, the technology is different.
Yes, sir. Yes, sir.
Because you are not melting the material, just you are adding the material by creating bond with sufficient amount of sintering process. So that is completely solid state welding.
Yes, sir.
So we cannot compare these two technologies. This is completely melted. There you are not melting.
Okay.
If there is no melting, there is no problem.
Here also some localized melting is there.
Localized melting.
Localized melting we can just have it right or not?
We can try. We can try. People are doing bimetallic also. We can do it.
Localized melting is that.
And that also creates problem also.
Yeah.
So that way you can see the compatibility between the two materials. So aluminum copper, aluminum steel, like that compatibility should be required.
Okay.
Right. Yeah. If it is over, so thank you very much for having patience.
So I must really thank you for your wonderful time and presence here. And I've been following the proceedings also. And I just went there to receive another guest. He is also arrived. And I request all the participants to utilize the services and the materials that the sir has delivered and try to put into the practice. And our special request is whatever is delivered by the resource person today, please take to the classroom. Then
That is required.
Yeah, that is required. Then you can it will be fruitful. Otherwise, outcome should be there and one to one. And please try to note down the important features and try to interact with sir through us or maybe directly if he allows. So try to use the material that is displayed here for your own academic purpose. So I thank you sir for your senior man coming over because I was knowing through the Murali that you had tough time to come over here. Maybe next time you plan comfortably and have a different session. Thank you, sir. Thank you very much for your time.
Because you are faculty members, no? Students also there. So how to extract the work from the students? That is a task for the masters or teachers. Nowadays very difficult. Even then we can extract. How? So what I did is for tech students, for advanced manufacturing technology lab, there are hardly 30 students. So initially I generate 30 samples given to them. So then objective is you can identify the nature of the sample, that is material, and process. That is two objectives. The first day they are very happy. Only two objectives, no? 3 months. Sorry was given only two objectives.